Thank you very much, Ming Sung, Professor Wu, for the very kind introduction. Ladies and gentlemen, it's really an honor to give this lecture today. So we are in the virtual space, but anyway, let's try to make the best out of this. We are talking about the universal hybrid electric vehicle. You see here a picture of a car in which we installed a new approach, a double E-drive approach, and that's a part I'm going to have a closer look in the lecture of today. And all of those at NCKU who maybe also are able to come to Darmstadt. This car is running on our local airport of the let's call it a small airfield of the Technical University of Darmstadt, where we have a good testing track to look for and care for those vehicles that we are working on. Now, personally, my background is mechatronic systems, and I want to start my lecture in introducing into vehicle technology and real state-of-the-art vehicle technology. At TU Darmstadt, we are working since more than 5 years on the what we call vehicle of fifth generation or vehicle 5.0. And you see here on the left-hand side how the generation steps have been developing. First, we had the motorization of the vehicles, very principally. Then we had auxiliary electrics, like the lights, like electric generator and electric motors to start the engine, but not as a traction machine, the electrical part. In the third generation, mechatronics started. The first mechatronic system was the anti-lock braking system of Bosch, starting in 1978. So this is more than 40 years ago that programmable mechatronic systems with software entered into the vehicles. And now we are approaching more and more digitalization. So that was the first step of digitalization. Now, the next step was that you have a lot of mechatronic systems which are connected. First step internally, adaptive cruise control is such a system, for example. And we're also going now to connecting the systems outside of the vehicle. We have things like Internet of Things and car-to-car connectivity. So that's the next thing which is going in the direction and giving new opportunities by digitalization. And the fifth generation now is self-learning or self-optimization. This means that if you release the vehicles for production, and if they go into serial application and they go into user hand, they are not conserving their attributes, their performance characteristics. They are changing their attributes by machine learning and self-optimization. And that's really another paradigm shift into the fifth generation technology. And let's have a look now to that fifth generation technology more closely. You see, there are digitalization aspects which are very important. Machine learning, I've just referred to this, but also with the connectivity, external connectivity, security, and privacy comes into play. We have human factors, which are very important. Acceptance and trust. What's the user behavior? And depending on the user behavior, do I have the right approach of the powertrain, for example? Do I accept the data usage? Do I have trust in privacy aspects? And also very important, what you see here, economy. The technology has to be affordable, of course. And a very, very important next step is ecology. We are struggling all over the world with the climate change challenges. And life cycle analysis of the technology is therefore, of course, very, very important to be considered. So these are all cross-sectional aspects, and you see we have on the columns 3 very interesting approaches which are directly related to vehicle technology. And you see here on the left-hand side optimization of the dimensioning of the parts. I'm not going to go deeper into this part. We have a spin-off which is working very successfully on that part today. We have the accepted automation technology, autonomous driving we want to go for. And this means somehow if we do machine learning during vehicle operation, we have to validate these approaches. And the approach we follow here is a virtual assessment of the automation in the field operation. So there is an approval process which is running while the vehicles are in user hand. And the focus of today, and now we're coming closer to the field that we want to deal with the lecture of today, that's real driving optimization of the powertrain, meaning that we want to consider really in a holistic way the whole mobility impact that we are having with our technology. So we want to make a short interaction process. You find here www.menti.com, and you see the code here. If you go on this on this page, then you can contribute in this poll. And I want to raise the question, which aspects are mainly considered to assess ecological effects of mobility today? So if you go on that homepage, you should be able to click which of the aspects you find: production aspects, fuel supply, tailpipe emissions, electricity supply, end-of-life impact. So if you are able to get access to this page, then you could contribute, and I see the first contribution is already there. So once again, I'm interested if you are ecologically assessing mobility of today and vehicles, and we're talking about drivetrains or powertrains today, what's the basic impact that we are considering? Is it the production phase? Is it the fuel supply phase? Is it the tailpipe emissions? Is it electricity supply? Is it end of life phase? So I'm showing the results now so far, and those who still want to contribute can still contribute. So let's have a look to these parts here. We have the production phase, which is today, according to the legislation we have in Europe. I'm not 100% sure about the legislation you have in Taiwan, but I know in other areas, production is not very much considered. For conventional vehicles, it's basically the tailpipe emissions. This meaning if you burn fuel and you generate CO2 emissions, then you basically emit carbon dioxide, and this means that the tailpipe emissions, that's basically the phase which you focus, where you have to focus on to be considered today. Fuel supply means basically generating the fuel from the crude oil, the process of generating gas, diesel, and this is also not considered. Of course, most significant part of today is really the tailpipe emissions. Also, in the European and the American legislation, electricity supply is not considered. It's always considered that electricity is without CO2 emissions, and also end of life is not considered. So, thank you once again for joining this process. Today, the tailpipe emissions are basically those when the vehicle is moving, which are considered. So now let's have an introduction to a universal hybrid electric vehicle. And at this point, I wanted to use my tablet to give you some notes. This slide, according to the abbreviations I'm going to use. So what you see here is ICE, internal combustion engine. EV is the electric vehicle. HEV is the hybrid electric vehicle. BEV is pure battery electric vehicle, no hybrid approach. REEV is range extended electric vehicle, meaning that we basically have a range extender to enhance the normally purely electric driving vehicle in its range. We have the plug-in hybrid electric vehicle where we are able to charge the battery from the electric grid. And we have the fuel cell electric vehicle. So these are the abbreviations now, which you will find on the following pages. And I am introducing the term universal hybrid electric vehicle now. And what does it mean now, the universal hybrid electric vehicle? And that's exactly what I want to join now in the next minutes. We have four main features that we consider with this vehicle. This vehicle means we are able to drive locally emission-free. That's very important for clean urban air and for reduced noise within the urban areas. On the other hand, we want to be flexible, that we are also able to go for long distances. And not only on the paper, this WLTC is the worldwide light vehicle testing cycle. So this is a test cycle which is used all over the world now. And this is not as tough as real driving, especially if you want to go real driving in winter when you need heating. So therefore, I say real driving at least 350 kilometers, also if you have low temperatures in winter. So these are two features, two requirements to the UHEV, which are related to driving. The third one is related to the infrastructure. You know, you a lot of times have an egg and chicken problem. What is first? First the technology of driving or first the infrastructure? Now, the universal hybrid electric vehicle can be charged with maximum 11 kilowatt, meaning that you can plug it at home. And for longer distance driving, because it's a hybrid, you can use available gas stations. So no prerequisite for new infrastructure. Very important. And to go for the outlook, and that's what I'm going to show at the end of my lecture of today, what we call sectorial integration. Do not only consider mobility, consider also power supply, consider buildings, consider other sectors beyond mobility, and where can you generate additional benefit with a vehicle. So that's the universal hybrid electric vehicle which we consider. And what we just already had a look to is that the evaluation of the ecological impact is basically done during the usage phase and with the so-called tailpipe emissions. What we are doing now, we are assessing the overall ecological impact, and we call this real ecological impact, considering carbon dioxide emissions during production, carbon dioxide emissions to supply fuel, carbon dioxide emissions to burn fuel during driving, carbon dioxide emissions for the electrical energy which is used for electric driving, and also carbon dioxide emissions when the vehicle comes to the end of its life and has to be brought back into the cycle or whatsoever you do with it, maybe going beyond recycling. You see, to make an assessment of different technologies, you find here a hybrid electric vehicle without plug-in feature, using petrol. You find a battery electric vehicle with one speed transmission, meaning one gear. A battery electric vehicle having multi-speed, having two gears. I'm going to come to this point a little bit later. A range extended hybrid, which is running in the serial hybrid mode. I'm going to go refer to this a little bit later. Here we have a plug-in hybrid electric vehicle with a specifically dedicated transmission. I'm also going to further detail on this a little bit later. One burning gas, petrol, the other one burning compressed natural gas. Yeah, so that's natural gas we are burning here. And then we have a fuel cell which has an additional battery having a plug-in function and using hydrogen. And then we have the pure fuel cell vehicle using hydrogen as it is produced today. That's the way you are using natural gas today to generate hydrogen. So these are studies we are carrying out. This is a reference to the year 2018 for a 10 or 12 years usage. And the important thing is you always have to consider the overall carbon dioxide footprint. And of course, you have to assume user profiles. We have considered here a specific cycle which is more demanding than the worldwide harmonized one, the WLTC, which I referred to on the last slide. And we consider a vehicle that is used by a family. A computer vehicle, one of the parents uses the vehicle for a 25 kilometers drive to work every day and back, therefore 2 times. And in the weekend and during vacations, they go also for longer distance driving, but most of the drives are below 100 kilometers, that's 98%. And this makes more than 80% of the overall distances are below 100 kilometers. So the electric range of 100 kilometers means that the car is mostly driving electric. Of course, you also have to consider the lifetime in order to see during production, the emissions you generate during production, what's the impact on the final mileage of the vehicle? And we assume, and this is quite a lot, 250,000 kilometers overall driving distance for that vehicle, 10 years driving. And if you look to the German, of course, you have to calculate this according to the country and according to the electricity supply you have there. And if you look now to Germany, the battery electric vehicle, because we still have a lot of coal power plants today, is not as good as, for example, a pure petrol vehicle with hybrid function. Of course, this is changing. If we are looking to the year of today, it's already reduced, but it's still not better than, and this is now the focus I want to go for. If you look to the hybrid vehicles, the plug-in hybrid vehicles, they show a much better performance on the carbon dioxide emissions, because the battery production needs a lot of energy and produces a lot of carbon dioxide emissions already before you even use the car. And that's the reason that you have to go for the overall assessment. And if we go to the future, when we are able to produce purely carbon dioxide neutral electric energy, then we can also consider the total energy demand. And you still see for the total energy demand, these plug-in hybrid electric vehicles, they are still in the range of pure battery electric vehicles, because the production of a battery, and if you need a huge battery to go for that high distance, this always means a lot of energy you already have to bring into the production phase. Now, what's the outcome of that general study? The outcome of this general study is that the pure battery electric vehicles and the fuel cell vehicles, which do not have a plug-in function, which go purely with the hydrogen, they lack positive effect today. And looking to the further development, tomorrow, we always have to consider and care about the overall resource efficiency. One is low carbon dioxide emissions, but also using resources, battery resources, lithium we need for it, and so forth. That's always what we have to consider. And we see plug-in solutions and electric driving for most of the drives is very, very reasonable. But if you scarcely go to long distance driving, then the question is, do you use a very, very big battery, or can you go for alternatives with hybrids using a combustion engine or a hybrid with a fuel cell? That's the basic introduction and the motivation to go on also considering hybrid vehicles and not only considering pure battery electric vehicles. Now, on that chart, you saw the abbreviation DHT. What does it stand for? That's what I'm wanting to go into now on the next slides. If we start with the conventional drivetrain, powertrain, we have an internal combustion engine and we have a transmission. 2 units, and let's assume we have a C-segment vehicle and consider about 100 kilowatt power of the carbon of the ICE, and let's assume torque capacity of the transmission of roughly 200 newton meters if we consider a petrol engine. Now, the hybrids, and I did not introduce that here, at this point, the hybrids can be parallel hybrids or serial hybrids. Now, if I'd been in the classroom, I would sketch that on the tablet. So now I have to do it with my voice. Parallel hybrid means that in parallel we add an electric machine and have two sources to generate the torque to drive the vehicle. That's the combustion engine and that's the electric motor, and the transmission is collecting those. If we have a serial hybrid, then we have a combustion engine which is propelling an electric generator to produce electricity, and this electricity is used in a second electric motor, which is the traction motor to drive the vehicle. So for the serial hybrid, you always need two e-machines. One as an e-generator driven by the combustion engine, and one to drive the vehicle. So there is no mechanical link between the combustion engine and the wheels of the vehicle. Now, a dedicated hybrid transmission is now a transmission which is not combining ICE and e-machine, as I was telling for an add-on parallel hybrid. It's a very specific design where you are not able to drive the vehicle without the electric machine. For example, no reverse gear. So you can only use the electric machine, turn it in the opposite direction to drive the vehicle in the opposite direction. And also some other features which are used, functions that normally are delivered by the transmission, they are used with the electric machine. So this means you have the ICE, you have the electric motor, but you can reduce the complexity of the transmission. That's a dedicated hybrid transmission. And we introduced the dedicated range extender transmission, which exactly belongs to the universal hybrid electric vehicle. Basically, we are driving the vehicle with the electric motors. We need an even simpler transmission because it's dominated by pure electric driving. And we still want to have a combustion engine, but not to define the driving performance. It's just to deliver energy when the battery is discharged and you want to go further to extend the range of the vehicle. Therefore, the DRT, and you only need the average power for the long distance driving to be delivered by the combustion engine. You do not need power to accelerate the vehicle, for example. You only need the average power, and this makes the combustion engine also much simpler. And the approach that we have been following now in our research at our institute is to go for a so-called two-drive transmission. That's for pure electric driving and is for hybrid driving. And this approach, the two-drive transmission, is going to be shown on the next slides. What you see here, with two electric machines and a multi-speed transmission, we are able not only to use one gear or just have one speed, which is today the standard for battery electric vehicles. You can generate further benefit using multiple speeds. I'm going to show that in a couple of minutes. And you can also use it for a hybrid vehicle. And for the hybrid vehicle, you consider and install the internal combustion engine in one of two subtransmissions. What does subtransmission now mean? That's what I'm going to show you on the next slide. You see here that simple sketch. That's a pure electric vehicle here, but it has two electric machines, not one 100% sized electric machine, two 50% sized electric machines. Both electric machines have a subtransmission. That's the upper subtransmission, that's the lower subtransmission, and they come together at one output shaft. And you see, you can shift the two subtransmissions here. They are both two speeds. We started with this idea more than 10 years ago with first projects, and then we also on the theoretical level moved forward. here we have a approach where one subtransmission is 2-speed, the other one is 1-speed. So you have a 3-speed overall transmission, and the focus was high RPMs, high engine speed, up to 30,000. We did not install it in the vehicle, but we already made some hardware for the test rig. Now, the focus of the talk of today will be this approach here. It's a 2x2-speed approach for a hybrid. You see, we have here a 2-speed transmission. In one subtransmission, we have also the combustion engine, and the other subtransmission only has the 50% electric drive. You see here again the two electric machines. And what you see here, that's the next step of this pure electric vehicle here, the same approach, but we now installed it in a vehicle, and we even for high-speed driving went up to 50,000 RPM for the electric machines. You see here the modular concept that with a general gear set up here, you can go for pure battery electric vehicles, and you can also go for hybrid electric vehicles. The range extended vehicles always have the plug-in function. I just repeat that once again, because mostly we want to drive electric. Only if we go for longer distances, more than 100 kilometers, without the possibility to recharge the battery, then we are using the combustion engine. Here you see now the detailed setup, gear set of that so-called dual electric drive with range extension, DEREX. Here we have a 3-cylinder combustion engine. We have these two electric machines, and you see, to install it in a vehicle, it's not so easy and straightforward. If you have a careful look to it, you see we need some intermediate gears here additionally to be able to install it in the vehicle according to package reasons. And what you also see, we have an additional final drive, which is considered here. So this is an approach we followed for the prototype vehicle in order to be able to install it in that vehicle. Now, how about the electric motors here? I was referring to a C-segment vehicle, roughly 100 kilowatts of engine power. And you see we have two electric motors here, roughly 50 kilowatt each. You see, we have in this vehicle, there was an already available combustion engine with 65 kilowatt of power. We can even go lower in future, but that was an already available combustion engine which we used here. And you see the powertrain output is up to 2,500 Newton meters at the wheels. And this is exactly the traction limit of a vehicle like this with front wheel drive. Higher torque on the wheels would generate slipping wheels. But you want to have this high torque to have good climbing possibilities, especially if you want to climb up on a pedestrian walk area, for example. Now, what is further important to consider? You see here now the two sub-transmissions. You see the blue one, which is connected to the combustion engine and to the electric motor 2. You see the yellow one, which is connected to the electric machine 1. We have these two sub-transmissions. You see the sub-transmission 2 can be shifted here. We can connect the machine 2 and the ICE to this gear pair here or to this gear pair here. And we can connect the yellow part with this shift sleeve also to the same gear pair, which is also used for the blue side. And here also the same gear pair can be shifted from the left side, from the yellow transmission. That's what we call a so-called coaxial gear setup, because you see that both sub-transmissions are coaxially positioned where the shifting is taking place. We have a pure electromechanical shift operation with shift drums. And these shift drums come from motorcycle technology. It's a very efficient and effective approach that we had here. But today we even go for the development and the research on even more sophisticated shift systems. What's very, very important is to use no friction clutches. Instead of using friction clutches, using dog clutches. We have no friction elements to synchronize at the shifting positions. We synchronize with the electric machine. So if we want to shift, for example, the yellow transmission, and we shift here from the first speed to the second speed. If we disengage the gear here, then we have to reduce the speed of the electric machine to be able to shift the second gear. In conventional drives, you have synchronizers, conical friction elements to do this. Here, we reduce the speed and synchronize the speed with the electromotor, and then we can have just pure dog clutches, no friction elements, so we improve the efficiency significantly. That's a big and very important part that we are considering. A very strong impact on the efficiency. A next part is we do not only want to have a very high drive-away torque of these 2,500 Newton meters, we also want to be able to go for a maximum speed of 180 kilometer per hour. That was the requirement in this project, which has been stated by the industry partners. So maximum speed of 180 kilometers per hour should be possible. And now, finally, you also see that this system is able to show parallel hybrid operation and serial hybrid operation. Parallel hybrid operation is very simple. We run the combustion engine, engage, for example, a gear here, and operate the electric motor here in parallel. Or also this electric motor with a selected gear and an NH gear on the yellow transmission also here. So you see, we can have very easily a parallel hybrid approach. But we can also show a serial hybrid approach. If we are neutral here in the blue subtransmission, so no gear engaged, then we can run the combustion engine to drive the electric machine 2. This is then the generator producing electric energy, and we drive the vehicle then with the electric machine 1. So it is capable, that system, of performing serial hybrid approach. For high efficiency, of course, we go for the parallel hybrid approach. But for some flexible and for some special situations, we can use the serial hybrid mode. And that's a strong point with respect to flexibility. And you will see a little bit later, then I will talk about so-called virtual gears. I'm going to introduce that in detail a little bit later. That's exactly where we then have to operate the system in the serial hybrid mode. Now, Having introduced the general idea and the general gear set, you see now, let's move to the proving ground. You see the vehicle running here. That's the C-segment vehicle. That's a Mercedes-Benz B-Class. And we installed here for that front-wheel driven vehicle this new drivetrain. And we want to consider now three very important aspects. We want to consider efficiency, we want to consider costs and complexity, and we want to consider driving comfort. Now let's start with efficiency. You saw that we can go with our approach, and that's the most of the drives we want to cover for pure electric driving. A range of about 100 kilometers is what we want to do, and we want to dimension the battery in the way that we can go for about 100 kilometers. With the two electric machines and the two speeds in every subtransmission, we can go for 8 different operation modes. You can go with the first machine in the first or the second gear. You can go in the second subtransmission for the first or the second gear. So the first 4 operation modes are if you just run one subtransmission, only one electric machine, either the first or the second. And then you can use the same operation modes, and then you can drive them parallelly. And you come up with, in total, 8 operation modes. And that makes the system very flexible. And related to efficiency, you also have a very strong point. If you have not one big electric machine, if you have 2 50% scaled smaller electric machines, you can operate the electric machine for partial loading in a more efficient operation point. That's a downsizing you have integrated in your approach, because at a lot of times you only have to use one electric machine. And now you see here, that's the so-called worthwhile harmonized light vehicle testing cycle. You find it here, it's 1,800 seconds. Here you have the city part, and you also go for a highway part where you speed up to about 130 kilometers per hour. That's a simulation here which is made, and you see there are only about 20% of the situations where you have to run both electric machines in parallel. Mostly you can drive with just one electric machine, and that's another point which is beneficial for the efficiency. So now, according to this, let's have a look to the efficiency goals and the efficiency objectives that we want to consider. And I want to go slowly through this chart in order to go step by step in the way that you can understand the approach that we followed here. Now, the bogie, the original part, is using a battery electric vehicle with one gear. And in order to be able to operate that one gear battery electric vehicle with a driver weight torque of 2,500 Newton meters and a maximum speed of 180 kilometers per hour, then you have a rather high speed range, and you need a very high power of the electric machine to be able to feed that operation. And if you look to a lot of battery electric vehicles of today, they have rather high power electric machines, because they are more introduced into the market from the high performance side. So they a lot of times have even more than 170 kilowatt power of the electric machine. But if we are focusing now real ecological impact, meaning also least electric consumption during driving, then we do not need a sports car. We are still considering about 100 kilowatt electric power as efficient to propel the vehicle. And on the other hand, according to the very big battery you need for this approach, there is also a high mass that has to be considered. So now let's have a look. That's the starting point. That's the state of the art. One-speed battery electric vehicles. The first step you can go for is going for the downsizing, because for the driving performance you do not need this high power. And if we are looking for the electric motor that's adequate for our driving situation, and of course we know that we do not fulfill then the launch requirement, the torque is lower than the request, then we can go for a significant reduction of the electric power consumption. Meaning really going for the adequate power we need is much better to just waste a lot of potential by having a too powerful electric machine. A next step you can go for is going for a two-speed approach. A two-speed approach now allows us to come up with the right launch torque, because for the low speeds you use a high ratio, and with that high ratio you are then able to bring the high drive away torque, but with that high ratio you are not able to go for the high speed. So you have two speeds, one to allow the drive away torque, and the second one with a lower ratio to go for the maximum speed. You see, with the two-speed approach, there is another reduction in electricity consumption. And if you finally go for the two electric drive approach, you can go for another % reduction. Now, the lag you have with that two-speed approach here, based on automated manual transmission technology, which is basically a manual transmission which needs torque interruption during shifting. It's the same as you drive a manual transmission, it's only robotized. This has the highest mechanical efficiency, but we have a lack of driving comfort here. And this is a point where I want to again share another poll with you. I'm moving here to the next one, again with a Mentimeter control, and I'm very interested in your consideration. Is this torque interruption, which is known from cars which have a manual transmission, and also those with an automated manual transmission, because all the things that for the manual transmission are done by the drivers, they are replaced by actuators. And therefore the question is, torque interruption, is that acceptable? Do you say this should be yes? I'm sorry, I made the wrong, it was German. Or is it not accepted? That's the question. Automated manual transmissions are used still very frequently for trucks and for long haul and coaches, buses, which are for longer distance traveling. And there are still some cars which are on the market which are some passenger cars, which are having automated manual transmissions. But in a lot of vehicles, they have been replaced by dual clutch transmissions, also for the very small cars. So thanks a lot for your consideration here. We see that 2/3 of you basically say torque interruption is acceptable, and 1/3 says no. We want to go in passenger cars for more sophisticated technologies, and that's basically also the approach that we have been looking for with our next research steps. I want to move to the next page, considering the cost effect. So the cost effect, if we want to be long range capable, these 350 kilometers with this cycle I was presenting, the Artemis cycle, which is a very demanding cycle. This means that for pure battery electric vehicles, you see here, you need at least 72 kilowatt hours battery. Or if you go for 2 speeds and a small electric motor, according to the efficiency benefit, you can go with 65 kilowatt hours to come up with a 35 kilometers, 350 kilometers overall range. The request is also for the hybrids now to be able to drive at least 100 kilometers pure electric. You see here the approach that we have been doing our research on. This just needs a 18.5 kilowatt hours battery to go for 100 kilometers, and a standard plug-in hybrid electric vehicle with a dual clutch transmission has not the same efficiency. That's also state of the art. It's a specific parallel hybrid, needs 20 kilowatt hours. And now have a look to the cost approach. These are the costs for the powertrain and the battery. And you see in this approach that for the pure battery electric vehicle, the costs are the highest because the battery is here calculated with 100 euro per kilowatt hour, and therefore the battery is very, very expensive. Of course, prices are falling now, are reduced, but at the moment, these 100 euro per kilowatt hour are a very reasonable approach still. According, and that's the DEREEX approach, we need more complexity in the transmission. There are more costs in the transmission, but we have a significant downsizing of the electric part, which is a little bit more if you have just one electric motor, like for the 2-speed approach here for the pure electric vehicle, which benefits, of course, from the smaller battery. But you have more complexity in the 2-speed transmission. That's the transmission part here. And you see the overall costs are the best ones for that approach. That was also a consideration we made. And here you also, sorry for clicking to this just right now. This is again the approach we have been talking about with this 100 kilometers range for pure electric driving we want to have. But intelligently considered, this system still has a reverse gear. The system still has a drive-away device like a clutch or a torque converter in future. This one has the clutches which can be used to drive away. So you see here the significant cost benefit, but this also brings a significant weight benefit with it. It's not only cost, it's about the same scale in weight, which is also important to be considered. Now, let's have in the next step a look to the comfort. Now, here we see on this chart how we shift the system. We start in the first gear here with the electric machine 1, which is driving the vehicle, and we are now shifting to the second gear, which is then to be engaged in the second subtransmission, and then the electric motor 2 is going to be driving with a second speed. So we disengage then this shift system here, this is the sleeve here, and we engage the sleeve here. Now, having a look to the slides here, to the diagrams, here you see the torque. The torque of the blue motor is the traction motor 1, and the red is the second one, which is not propelling at the beginning. You see here the speeds. The blue subtransmission, the motor 1 is speeding. The other one is just slightly moving according to some drag torque, which is relevant there. And here you see the shift drum position, the angle, in order to see how the gears are engaged. Now, what is the first approach? You see here, we move, that's what I already explained, to the second subtransmission, and then we engage this gear here and disengage that part. So the approach we are going for is that first we have to be able to engage the gear in the second transmission. We use the electric machine there to synchronize. You see this? There is this up speed in order to be able to have the right synchronized speed. And then if it's reached, then we are able to move the shift drum of the respective subtransmission and to engage the gear. Now the gear is engaged. We have a very, very short torque blending, handover of the torque. So we reduce the torque of the blue part and we increase the torque of the red part. And if this is done, then we have to use the energy which is still in the inertia of the blue part here of the motor 1. We use this to recuperate the energy. You see here it's speeding down. We are bringing that speed down, and then we are able to engage then when the speed is synchronized that gear. Sorry, that there was a mistake I was telling here. Of course, in order to be able to do this, we first have to disengage the gear, and this is basically done here. It's disengaged here, and when it is disengaged, then we synchronize again, we recuperate the energy, which you see here, and that's also very important to have a very high overall efficiency. So I repeat again, we first have to synchronize the second transmission where we want to shift to. We are doing this with the electric motor. When we have the synchronization speed, we engage the gear with the actuation system. Then we hand over the torque. Then we have to disengage the original gear in the original first subtransmission. Then we do not want to lose the energy, the rotation energy. Therefore, we use the electric motor 1 as a generator to break down the motor and to recuperate the energy. And then the shift is done. And you see measurements which have been taken in the vehicle, and you see you are not able for that vibration dose value, that's a specific value, assessing the performance. And here you see the acceleration. You do not see any change in this acceleration during the shift. And we can assess here also with a group of experts which have been driving with the vehicle that the shift here is not perceivable. You cannot realize that the system is shifting. It's also because the electric motors are not audible. They are very silent, and therefore it's the perfect shift you can approach. Now, looking for a higher load shift, and a higher load shift is done here. For example, you see both electric motors are driving the vehicle in parallel. Both are running over the first gear stage. And now we move and change in the first subtransmission for the electric motor. We shift to the second gear. That's what you see here. So this sleeve here is disengaged and this one is engaged. And therefore you see such a shift pattern. What are we doing during these shifts? We have to ramp down the torque of the electric machine 1, do the shifting, disengage here, engage here. Of course, in between we have to synchronize and then we engage again and then we can ramp up the torque again. And what you see here, up to 50% of the driving torque, we still can hand over from one subtransmission to the other. As soon as we have a higher torque, we have a torque reduction during shifting. And what you see here, this is this vibration dose value. This is this criterion which is used also in the literature to evaluate the acceleration smoothness of a shifting. And you see automated manual transmissions. Automated manual transmissions are basically having a very rough situation. Automatic transmissions, AT stands for automatic transmission. This is a planetary gear set in conjunction with a torque converter. That's the classical automatic transmission, which is known and used for decades. The dual clutch transmission is basically a lay shaft transmission with 2 sub-transmissions and 2 clutches. And this is the further evolution of a manual transmission, a automated manual transmissions, and basically 2 automated manual transmissions in parallel, one with even gears, the other one with odd gears, and then you always hand over the torque from one of these sub-transmissions, each having a clutch, to the other. I'm not going into detail on this. You can have also a look in the internet, the general description of a dual clutch transmission procedure. It can be found there very easily. Now, what we find here, due to the torque reduction we have to go for, it's not a torque interruption, it's a reduction. The comfort is reduced if you go for higher acceleration. And our next idea in the next project is now to very shortly overload the machine which is still running during the shift, which is the electric machine 2 here. If you are just able in 3, 4, 500 milliseconds to significantly overload that electric machine, and this is feasible with the electric motors because their limit is only thermally given. If you are able to even raise the current on a higher level, if your power electronics allow this, then you can go for such an approach. And then our intention is to bring these perfect shifts to a higher level of acceleration performance. Now, you see here, we already have a good performance, rather good performance, but still we're not satisfied. Research needs also higher challenges, and that's the approach we want to go for. Now, we are talking about acceleration and shifting comfort. And according to this, it's also relevant to consider acoustic effects, because the combustion engine is audible. And here we have SPL, stands for sound pressure level. Please make a note on this that you are aware, sound pressure level. That's the measurement, of course, the measured entity to assess the noise. And we also want to consider this, and have to consider this. In the vehicle, in the approach I just presented, we have a two-speed approach, and the step change for this two speeds is rather high. We have a ratio between the first and a relation between the first and the second gear of more than 2. That's the ratio step. And this is not common for combustion engine drives. This is basically very good for the electric drive, but we see now there are some challenges which have to be considered for the hybrid drive. You see here, that's a normal sound pressure level curve of a 7-speed dual clutch transmission. Now, having a look to this DREX approach, you see, according to the high ratio step we have here, the noise driving in the first gear gets rather high, and related to comfort is not acceptable. If you shift somewhere here, you cannot go for lower speeds. Especially you also maybe have some booming noise if the speed is too low. So you have to shift somewhere here, and you see you are significantly higher than the levels you normally accept for combustion engine vehicles. Now, what can you do? And now we are in that flexibility area of this approach. We can use serial hybrid virtual gears. We're just driving the system because that's a partial loading approach. That's not on the full load. On the full load, you have no problem with a loud engine. This is something in partial load. So just driving the vehicle with one electric motor is okay. And therefore, in order to give the car the feeling of a conventional multi-speed combustion engine vehicle, we introduced virtual gears with speeds directly in between the first mechanical and the second mechanical gear. So we have a gear here, the first virtual gear is between the ratio of the first gear and the second gear, and the second virtual gear is lower than the mechanical second gear ratio. And with this approach, you can find now a way that you can combine the approach and at least at 20 kilometers per hour come up with the same noise level. If we are below, we have some specific aspects in our prototype vehicle that the engine could not go for a very low idle speed, and that was the reason why we had higher sound pressure levels in this area. But with a virtual gear, you see, especially in this area here, where you normally have comfort impact, the problem can be solved. But of course, these virtual gears, they lead to a reduction of efficiency. Serial hybrid mode is having mechanical energy, converted it into electrical energy, then using the electric energy, converted back to the mechanical motion of the vehicle. So mechanical, electric, mechanical. This is a 2 times conversion, which is not good. So it's better to use the parallel hybrid mode. And you see, we lose 4 to 6% in fuel consumption efficiency. And that's, of course, an approach which has to be tackled in future in the next step. So having a look again and summarize the lecture, we saw if we want to combine high drive-away torque with the respective maximum speed, a multi-speed approach is very, very reasonable. With this multi-speed approach and that 2 electric motor drive, we have a very, very high efficiency during electric driving. That's basically benchmark in general we want to achieve, because the overall vehicle mass is low compared to a long-range capable pure battery electric vehicle, and therefore we want to go for really benchmark on the pure electric consumption. We have, on the other hand, the possibility to go for long range, still with reasonable carbon dioxide emissions here. We have that high driving comfort because we have no torque interruption. We have gear shifts which are perfect and not perceivable as long as the overall acceleration of the vehicle is not too high. And compared to the state-of-the-art single-speed battery electric vehicle, we are even able to reduce costs, and therefore we find and we think that that universal hybrid electric vehicle is a very interesting approach. We started just in April a next project, improving now all of the things we learned. This is a project together with Hyundai and Continental, Vitesco, and AVL. These are really famous companies in the area of vehicle development and vehicle engineering, and we just started with that project, and we call that DE drive for long range. And the improvement is going in the direction. You already see the general design of this sketch here. We have now 4 mechanical speeds. We are able to connect the combustion engine to both sub-transmissions, and we do not need intermediate gears. We also have from the electric motors only 2 gear meshes to the wheels of the vehicle. So this is also another significant approach to improve the efficiency. We want to improve by another 3% by really making a much simpler combustion engine and increasing the integration level of the overall approach. We also see another cost reduction potential of 5%. And we are going for a compressed neutral natural gas combustion engine because the CO2 emission is even better. And there is also a very nice approach to move in future to e-methane, meaning that we use hydrogen and make some longer carbon chains and have synthetic methane, which allows us finally to even operate the overall car carbon dioxide neutral. And to come up to the outlook, which is my last slide here, looking for the sectorial integration and looking for the universal approach, the 4th item, you can not only use your electric vehicle as an energy storage device with a battery for the electric grid, you can also use it when you have a hybrid system and you have the combustion engine. You can also use it as a power generator, a mobile power plant. When it's parked at the house or maybe at a factory, you can really go for a smart grid, smart home, or smart factory approach. Especially if you look to the German power plant approach, Germany is going to jump out of nuclear energy and out of coal. And therefore, wind and sun are the most energy sources, and there are in winter so-called dark doldrums, no wind, and only very low daylight and very short daylight periods. Therefore, you need backup power plants, which are normally gas power plants, and the vehicles can serve as an additional power supplier in those cases, and this even opens up new approaches with respect to business, new business models, and this basically shows us universality can be beyond mobility for vehicles, and that's another step we want to take in research. And this is now the final statement of my lecture of today. Thank you very much for your attention. Bye.